This is a quick explanation of the multiple negatives ranking loss that can be used to train sentence embeddings from only positive pairs of texts. So sentence embeddings are typically used for similarity tasks, with one common use case being semantic search. So with semantic search, it allows for searching based on meaning and not on lexical overlap. So that means if someone has a query about finances, the results should have documents about money, about budgeting, and those documents don't necessarily need to explicitly mention the word finance. So to start, here's a quick walkthrough of how sentence transformers, sentence embeddings are produced. So the text will go into the tokenizer, it'll get tokenized, those tokens will get turned into embeddings. Those will go through the transformer. Now you have contextualized embeddings, and then you'll average all of these through mean pooling to produce one sentence embedding. So this means if your sequence is 64 tokens, there'll be 64 token embeddings at the output, but then you'll only have one sentence embedding. So it doesn't matter how long your sequence is, you'll always have one sentence embedding. Now, the length of the sentence embedding is equal to the hidden size of the model, and a typical hidden size is something like 768. Now, this sentence embedding is meant to represent the meaning of the sequence that was put into the model. In terms of data, you'll only need positive pairs of similar texts. So, like before, you'd need some pair of texts like finances and budgeting. Ideally, if you're doing this for search, you'd have a query with a few words and then a document with a few words. This works much better for sentences and less so for single words. So now we're looking inside a single batch when we're training these using the multiple negatives ranking loss. So I mentioned before, queries and documents, it can really be any two types of pairs. So now I'll switch to just A and B. And here I'm showing that for group A, your batch size will be n, so n texts will go in, n sentence embeddings will be made, and then you'll stack all of these sentence embeddings to form a stacked embedding matrix that's n by h, where n is the batch size, h is the hidden size. So you'll do the exact same for the other group. Now I show the group B as having a batch size of m. N and m are usually the same. They don't have to be the same. And so when you put this all together, you'll have two matrices, n by h and m by h. Now what you want to do now is calculate the similarity between each of the embeddings in A with each of the embeddings in B. And as you do each of these, you'll end up with an n by m matrix indicating the similarity between the embeddings of group A with the embeddings of group B. So at row I, column J, you'll have the similarity between embedding A sub I and embedding B sub J. So the similarity metric you want to use, or a commonly used one, is cosine similarity. And this is a measure of how close the two embeddings, the two vectors, are pointing in space. So if they're pointing in exactly the same direction, they'll have zero angle in between them, and cosine of 0 will be 1. This is the maximum cosine similarity score. If they're pointing in opposite directions, the cosine similarity score will be -1, because cosine of 180, cosine of pi, is equal to -1. So this is the minimum cosine similarity score. So in reality, with your embeddings, you'll have many more dimensions, and your score will be somewhere between -1 and 1. One thing to note is that the magnitude of the vectors does not matter. It's only about the angle in between the two vectors. So ideally, you'll have very high values along the main diagonal and very low values everywhere else. And so what I'm showing you would be the ideal case after taking the softmax of each row, indicating that embedding A1 is very similar to embedding B1, A2 and B2, A3 and B3, AI and BI. And because each of those with the same index, AI and BI, are positive pairs of similar text, we want to maximize those similarity scores, so they should be as close to 1 as possible, and everywhere else should be as low as possible. So in reality, you'll have logits and it won't be perfect. And so when you're calculating the loss, what you'll be doing is going row by row, calculating the cross entropy between the logits and the ideal labels. So you can think of this as single label, multi-class classification. And so your model predicted a bunch of scores, and the true class will be the index along the main diagonal. So for row 0, it'll be 0, row 1, it'll be 1, row 2, it'll be 2. And then you'll just use regular cross entropy to calculate the loss. So you'll do that at each level. You'll be averaging all those together, and that will be the loss that you use. The reason it's called multiple negatives ranking loss is because for each embedding, it's assumed that there's only one positive pair and everything else is considered a negative. So that's why each one will have multiple negatives. And so what this does is rewards the model for reducing the angle between the embeddings of positive pairs of text and maximizing the angle between non-pair.